Welcome back, everyone. Hope you're having a good day. Today, we're going to progress beyond the ramjets and add a compressor and turbine to describe the turbojet system. But first, I'm actually going to spend some time going through a ramjet example. The first iteration of this class, I actually didn't even have these examples because I was in such a hurry at the end of the course. But I think it is important that you guys have at least one example of each of these propulsion systems, especially for the homework. It'll help you get through those. So for this example, we're going to have a ramjet system that is operating with a shock upstream of the system. Okay, so we have our inlet just like we've been describing in the last lecture. Then you have the burner, and then converging nozzle at the exit. Okay, and then there's a shock upstream, a detached normal shock upstream of the ramjets. And then we have our free stream conditions upstream of it with a free stream Mach number of 1.5, flow going directly at the engine here. As far as given values, we know that the temperature after the burner is 1400 Kelvin, or I should say the stagnation temperature. We know that the temperature upstream is 216 Kelvin, that's the static temperature. And the static pressure upstream is 2 times 10 to the 4th pascals. Okay, we're going to make a range of assumptions. First, we're going to assume that the engine is designed such that M3, the Mach number just upstream of the burner, remember that station 3 is here, station 4 is here. Here we have the exit. Station 2 is right at the edge of the inlet. The throat of the inlet is station 1.5, and then station 1 is right at the entrance. But at station 3, the Mach number is approximately 0. We're also going to assume that our working gas is air. So gamma is equal to 1.4, R is equal to 289 joules per kilogram Kelvin. And then we're going to assume that the fuel ratio, fuel mass flow rate ratio is very small, much less than, not 0, but much less than 1. Okay, so we're assuming that's very small. And then the goal here is that we want to calculate the non-dimensionalized thrust, T over P naught A naught, and the area ratio A naught over AE when the flow is essentially choked at the nozzle exit when ME is equal to 1. Okay, so that's the goal. Now, I want to say that there's a general flow to these types of questions, these propulsion questions, okay? And if you follow this sort of flow of reasoning, you'll at least get a good start to every single one of these problems. So first, you want to note where the stagnation temperature and the stagnation pressure remain constant. So for instance, in this case, we know that the stagnation temperature is not going to change across the shock. So TT naught is equal to TT1, which is equal to all the way up to TT3, but TT3 is going to be less than TT4, right? Because that's where the burner is injecting heat into the flow. And then TT4 is because we're assuming that there's no shocks elsewhere in the system because it's not denoted as such. We know that TT4 is the same as TTE at the exit. Okay. Now, as far as the stagnation pressure goes, we know that the stagnation pressure is going to drop across the shock. So PT naught is less than PT1. But then you have isentropic flow all the way up to PT3, or station 3. So PT3 is the same as PT1. Now, normally across a burner, you are going to have a drop in stagnation pressure, but it's very, very small, especially when the Mach number at station 3 is really small. So that assumption that we assume that Mach number at station 3 is equal to 0, that actually tells us that PT3 is equal to PT4 as well. So that's that small Mach number at 3 assumption that allows us to sort of, it leads to this assumption that the pressure drop, stagnation pressure drop across the burner is 0. Or sorry, it is 0, so therefore the ratio between those two pressures is 1. And so the stagnation pressure remains the same throughout the system beyond that normal shock. Okay, so that's the first thing you want to do. I would for every single one of these problems, I would kind of write down these two lines here, because it'll help you if you wanted to relate two stations that like the inlet and the exit, for example. You know that at the exit, the stagnation temperature is equal to a known value, TT4 in this case. So it makes it a little bit easier when you know where all those things are equal. Okay, so that's the first bit of the general flow here. The second is to relate key stations using mass conservation. And that's that fancy mass conservation equation that I showed to you. But when you assume that the mass flow rate, that it's a calorically perfect gas throughout the system, for example, then that means gamma is not going to change. Then you can use this relationship where you end up with just like, here we'll just say we're looking at station 1 and station E, for example. All the constants out front of that fancy thing go away, and you can end up with something like this: PTE AE over the square root of TTE FME. So there's a couple of assumptions here. One is that you have a calorically perfect gas, so all the gammas and R's that were involved in this expression cancel out. But another thing is that you have, in this case, since we're relating across the burner, we're also assuming that F is small. So you have to keep in mind the fuel mass flow rate when you make this assumption, because really what you're doing here is this is the same thing as saying the mass flow rate at station 1 is equal to the mass flow rate at the exit. Okay, and most of your useful relations are going to be obtained using this mass flow rate equivalence here. So that's one thing with this mass flow rate equivalence in terms of the stagnation pressures. And then the last thing that you do, one of the general flow steps that we won't actually do in this case, but will become important for the turbojet and the turbofan, is that you relate the various components of the engine. Like today we'll talk about the turbine and the compressor, for example, with an energy balance. Okay, so just keep that in mind. This right here, you can think of as your general flow. And if you follow these steps, you'll at least get a good start on just about any problem that involves these propulsion schemes. Okay, so let's go ahead and actually do this problem here that we have set up. Now, the first thing that we can do is whenever you're asked for an area ratio, okay, like what we're asked for here, that should tell you in your mind right away, should just scream in your mind, I better do a mass balance between those two stations. Because that mass balance, I can easily pull that area ratio out of that. So the first thing that we're going to do for the problem is to use mass conservation between station 0 and the exit. 0, and E. Okay, so just like I wrote down above, it just looks like this because we're assuming that F, lowercase f, is very small, and that we have a calorically perfect gas. We can just write this right away. F of m naught is equal to PTE AE over the square root of TE F of ME. Okay, and so, like I said, that allows us to easily rearrange for A naught over AE, and we have PTE times F of ME, which we know that ME is equal to 1, right? That's one of the givens. So F of ME, which is equal to A over A star, is equal to 1 itself, right? Then we have PT naught times F of M naught in the denominator. And then we have this multiplied by this quotient TT naught over TTE. Okay, so now we can actually hunt down a lot of these values. So first off, let's do some calculation. We know that TT naught and PT naught can be calculated using the upstream Mach number and the static pressure values, using our standard relationship between the static and stagnation properties. Okay, in this case, TT naught is equal to 313.2 Kelvin, and then PT naught is equal to P naught times 1 plus gamma minus 1 over 2 times M naught squared times gamma over gamma minus 1, and this is equal to 7.342 times 10 to the 4th Pascal. Okay. We can also just calculate F of M naught. It's you can go look in the table and invert the value if you're using the textbook. You can also just punch in the actual formula that was written down in the previous lecture into a calculator and do it that way. But in this case, F of M naught, or F of 1.5, is equal to 0.8502. Okay, and then we know that TTE, because we did that check before, we said where is the stagnation temperature remain constant. We know that TTE is equal to TT4, which is equal to 1400 Kelvin. Okay, so we have almost every value here. We just need to figure out PTE. So need PTE. And so that is where we look up here. So we have that assumption that pi b is approximately 1, right? So that PT3 and PT4 is the same. And we know that PTE, we can backtrack all the way through the engine and see that it's going to be the same as PT1. Okay, so need PTE. We know assumed pi b was approximately equal to 1, which tells us that PTE is equal to PT1. Okay, and then PT1, well, we can get that using the normal shock relations. Use normal shock tables. Okay, so in the normal shock tables, for a Mach number of 1.5, PT1 over PT naught is equal to 0.92979. Okay, just look that up in the table. And then we have everything we need to calculate the area ratio. A naught over AE is equal to PT1 over PT naught times F of M naught times this quotient TT naught over TTE, and that value ends up being 0.5173. Okay, so that's one part of the problem down. Now let's calculate the non-dimensionalized thrust. Now thrust. So the thrust equation in this case is P naught T over P naught A naught is equal to gamma M naught squared, and this is the general non-dimensionalized thrust formula when you have a very low fuel mass fraction, or lowercase f. So it's V over V naught minus 1 plus AE over A naught times PE over P naught minus 1. Well, we already have A naught over AE, right? So we know what that is already. We know what P naught is. That's given. We know what M naught is. Okay. And so first off, we should decompose that velocity fraction and write it in terms of the Mach numbers. You'll almost always be doing that. So that just becomes ME over M naught times the square root of TE over T naught. Okay. Once again, using that calorically perfect assumption. So now we know what ME is. It's 1. We know what M naught is. We know what T naught is. It's given. So we just have to calculate TE here. And we also, just like we showed on the previous line, we just have to calculate PE to get this term all wrapped up as well. Okay, so let's go ahead and do that. PE, we can just calculate as PT1, right? Because PT1 is the same as PT at the exit. That's times 1 plus gamma minus 1 over 2 raised to the power of minus gamma over gamma minus 1. That's because ME is equal to 1 here. So that's I just went ahead and subbed in that value. What you end up with here is 3.606 times 10 to the 4 pascals. Okay, so that's what PE is. And then TE is equal to TT4, because TT4 is the same as TT at the exit, times 1 plus gamma minus 1 over 2, all of that raised to the negative 1 power, is equal to 1167 Kelvin. And then with those two values, we can write what the final thrust is, in this case, non-dimensionalized thrust, I should say. In this case is equal to 3.283. Okay? So that's the solution to this example problem. Okay, but the big takeaway here is really this general flow. If you can do those 3 steps with every single one of these types of problems, you'll get pretty close to, or you'll get a good start on the problem, like I said before. Okay, so that is that example for the ramjet. Now let's kind of move on to the turbojet. But before we do that, let's talk a little bit about, let's recall what the thermodynamic efficiency of the ramjet is. So recall that the thermodynamic efficiency of the ideal ramjet was equal to 1 minus T naught over TT naught. Okay, and we can actually just write that in terms of the Mach number. That's 1 minus 1 over 1 minus gamma minus 1 over 2, M naught squared. And if we simplify that further, we get gamma minus 1 over 2 times M naught squared over 1 plus gamma minus 1 over 2, M naught squared. Okay, this should be gamma 1 plus right there. Okay, so looking at this, we can actually see that eta approaches 0 as the Mach number goes to 0. So as you go to lower speeds. And the reason why this is because the engine is using the inlet to compress the flow prior to combustion. In general, effective combustion requires high pressure and low flow velocity. So therefore, like a lower entrance Mach number. So if you have that lower entrance Mach number to a Rayleigh flow process, you reduce the PT losses. And if you look at, for example, the Rayleigh flow tables at the back of the Zucker and Viblar's textbook, you can see that P over P star, which is really telling you, or PT over PT star, which is really telling you how much the stagnation pressure is going to change between a certain state, and then if you add more heat all the way up to the sonic velocity, you can see that PT over PT star actually doesn't change very much for all of the small entrance Mach numbers, like between m equals 0.1 and m equals 0.15, for example, the PT over PT star value doesn't change very much at all. It's like very flat. And so what that's telling you is that for a low entrance Mach number, your stagnation pressure actually doesn't change very much throughout that Rayleigh process. Okay. At most, it's going to be like 20% or so, because I believe that the PT over PT star for a low entrance Mach number is around 1.2. So, so you can that's sort of a ad hoc explanation, but that's what's going on there. You can look at that to rationalize that yourself. But in general, this is why we always assume that the pressure drop across the burner is approximately 0, and that the pi b is about 1. Okay. So, but anyways. As you go to lower speeds, that inlet cannot do this compression for you. And so to overcome this, you need to add a compressor to compress the air at low Mach number. And then that's where we get to the turbojet. And we're going to describe the ideal turbojet here. One thing that happened last year when I taught this class was that people pulled formulae from this lecture when there were not when the problem was not ideal, so there was a shock in the system or something for the turbojet. So be careful. What we're about to discuss here is a turbojet operating in the ideal case. Okay, so what does a turbojet look like? Well, it's very similar to the ramjets. Where we have the inlets and then a converging, diverging nozzle, and then we do still have a burner. But now, flanking the burner on both sides, we have, and you saw this when I drew the turbofan for the engine labeling, we have a compressor and a turbine connected by a shaft. So station 2 is entering the compressor, station 3 is leaving the compressor, entering the burner, station 4 is leaving the burner, entering the turbine, and then station 5 is exiting the turbine. Station 7 would be the start of the nozzle, I guess. Usually not, unless there's an afterburner, not really much going on there. Station 8 is the throat of the nozzle. And then station E is the exit of the nozzle. And then we have station 1 here, and then we have our free stream station out there. Okay. In general, we're going to assume that there are no shaft losses. So the energy balance across the shaft is the following, where we have m dot A plus m dot F, including the fuel mass flow rate in there, times HT4 minus HT5. So that would be the energy supplied by the turbine, okay? So that's, we're looking at the change in enthalpy across the turbine, is equal to m dot A. So now a compressor doesn't have the fuel passing through it, right? It's before the burner, and the burner is where the fuel is injected. So HT3 minus HT2. So the energy that you're pulling out of the turbine is what is being injected into the flow by the compressor. Okay, so the HT3 minus HT2 is how much the flow is changing, how much energy the flow is gaining across the compressor. Okay? The reason why HT4 and HT5 are flipped here, it would be almost better to put all these terms on the same side because we want them to sum to 0. But that's why the turbine part is what's flipped here. Okay, and then we also have the burner energy balance, which is m dot A plus m dot F, times HT4 is equal to m dot A HT3 plus m dot F HF. Okay? And so we can actually sub these terms in to get an overall energy balance, including the burner, to get m dot A plus m dot F times HT5, which is equal to m dot A HT2 plus m dot F HF. Okay? So for the ideal, and then we're talking about the ideal turbojet here. So there's no shocks between 5 and in the exit, and there's also no shocks between station 2 and the free stream. So these things, this is actually equal to HTE, and this thing is equal to HT naught. Okay, and that this kind of is our overall energy balance. So now let's to illustrate what's going on here, to kind of be able to especially have a nice comparison with the ramjet. What we're going to do is we're going to calculate the thermal efficiency of this system. Okay, so the same idea where you have you're looking at you know, the heat, the rejected heat minus the well, in fact, actually, what we're starting with here is the propulsive. I can't remember the actual definition right now. Actually, I think it was like jet power divided by the amount of heat injected due to combustion. And then we wrote the V squared term in jet power by we split it up into the total enthalpy and then in the static enthalpy. You can go back to that lecture to make sure I'm not making a mistake here. But it's m dot A plus m dot F times the quantity HTE minus HE. So that normally would be VE squared over 2. Minus m dot A times HT naught minus H naught. Okay? And then the denominator is m dot A plus m dot F times HT4 minus m dot A HT3. And this thing is the heat injected due to combustion, which is just m dot F HF. Okay. So again, this is just like jet power divided by total heat injected due to combustion. That was the definition of the thermal efficiency. We can use our energy balance where we've replaced HT5 with HTE and HT2 with HT naught, and make some substitutions here and get m dot A plus m dot F times HT4 minus m dot A times HT3 minus quantity m dot A plus m dot F times HE plus m dot A H naught, all divided by the same denominator as before, m dot A plus m dot F HT4, whoops, HT4 minus m dot A HT3. Okay, and then just doing a little bit of algebra here, we can take out the 1, and then you have m dot A plus m dot F HE minus m dot A H naught over, same denominator, m dot A plus m dot F HT4 minus m dot A HT3. Okay, and then let's pull out some of the values here to non-dimensionalize. So then we get 1 minus H naught over HT3. Okay, and then we have 1 plus F HE over H naught minus 1 over 1 plus F HT4 over HT3 minus 1. Okay, so we pulled out the mass flow rate of air times HT3 on the bottom and then times H naught on the top. And then we can assume that we're dealing with a perfect gas here and factor out the specific heat capacities, and we end up with 1 minus T naught over TT3 times the quantity 1 plus F times TE over T naught minus 1 plus F T4 over TT3 on the bottom. Okay, and so now we're dealing with the ideal turbojet here. So stations 0 to 3, we're going to assume that the in fact, this is a very key assumption. We're going to assume that the compressor and the turbine operate isentropically. Okay, so assume compressor and turbine operate isentropically. And what that means is, in effect, that we can write TT. Well, really what it means is that the stagnation temperature ratio across the turbine is equal to pi c raised to the gamma minus 1 over gamma. Okay, so that would be like that's for the compressor. Same thing for the turbine. Okay, so that's what we mean by isentropic relationships between the two. But what that results in this case is that TT3 over T naught is equal to PT3 over P naught raised to the gamma minus 1 over gamma, and then TT4 over TE, so this is across the turbine here, is equal to PT4 over PE raised to the gamma minus 1 over 2 over gamma. I don't know why I said 2. Gamma minus 1 over gamma. Okay? And then we'll also make that assumption that the burner is ideal, right? So pi b, which is equal to PT4 over PT3, is approximately equal to 1. And then we're also going to assume that the flow is fully expanded. Assume fully expanded, or in other words, that PE is equal to P naught. Okay, and with all of those assumptions put into effect, that implies that TT3 over T naught is equal to TT4 over TE. Okay, and what that does is it makes this last thing up here on the top right, it makes this whole quotient go to 1. Everything cancels. And so the thermal efficiency of the ideal turbojet is equal to 1 minus T naught over TT3. So the temperature entering the burner. Okay, which we can write in terms of our engine ratios, engine parameters, as 1 over tau R times tau C. Okay, so one thing to note, which is the reason why we kind of got this result, is you can see right away that if we take TC to 1, in other words, you're literally taking the compressor out because it's not causing any sort of compression at all, it's not having any effect, then you end up with a ramjet. You recover the ramjet, which is good. That means that our analysis is sound. And then you can also note that if TC is less than 1, then the thermal efficiency is not equal to 0 at Mach number equal to 0. In other words, it's not equal to 0 where not equal to 0 where m naught equals 0, which is the same as tau r being equal to 1. Okay, so we solved our problem, right? We noticed this problem that when we went to low Mach numbers, our thermal efficiency was going to 0 for the ramjet. In this case, we don't get that. Okay, and then it's basically another sort of Brayton cycle. Okay, and we can actually draw how this looks, you know, which is how you can see it's a Brayton cycle in these thermodynamic diagrams. Let's say we started station 2, then we go up to station 2 T. I'll actually just draw the stagnation states right here. 3T, you go up here to 4T, and then station 5 is here, 5T. This is the exit, and then you go back to 0. Okay, we're going in this direction. And then this is where you have Q in. This is where you have the Q rejected. Okay, and then for completeness, we'll add the PV diagram as well. So the PV diagram, you have station 0 here, goes up through station 2T to station 3T, across to station 4T, down this way, to through station 5 to the exits, and then flat. And then that's where you get your Q rejected and your input Q there, where your burner is. Okay, so we're assuming that the stagnation pressure is remaining constant across the burner. You can see that there, for example. Okay, so that is a little bit of the thermodynamics of the ideal turbojet. Now let's go ahead and calculate the thrust. Now we're really going to do it just in terms of the engine parameters, kind of like we did at the end of the last lecture for the ramjets. But again, I want to caution against using the formula that we're about to develop in your homework without checking to make sure that you are indeed dealing with the ideal turbojet. Okay, so in general, we want T in terms of our engine parameters. So for a perfectly expanded turbojet, we have T over P naught A naught is equal to gamma M naught squared times 1 plus F times VE over V naught minus 1. Okay, and then of course we're just we're gonna replace V over V naught by ME over M naught times TE over T naught in general. Okay, now we're gonna go full ratio notation here. So bear with me. We can write PTE as P naught times pi R times pi D times pi C times pi B times pi T times pi N. Okay, so that's your stagnation pressure drop across, do your reference ratio, then the diffuser, the compressor, the burner, the turbine, and the nozzle. Okay, so all of your pressure ratios here. Now we know that we're assuming perfect expansion in isentropic flow in the nozzle and diffuser, and we're assuming the Mach number upstream of the burner is small. So that tells us all across the board that first off, PE is equal to P naught. So that's the perfect expansion assumption. We also have that pi D and pi N and pi B are all equal to 1. Okay, and that's isentropic flow and the nozzle and diffuser, as well as the that ideal burner assumption. Okay, so then things get real simple. So if we proceed from here, we end up with, first off, we can write PT itself in terms of PE times 1 plus gamma minus 1 over 2 ME squared times gamma over gamma minus 1. So that's just what PTE is. We can write it in that form. And then we can bring this thing over with all of these assumptions incorporated. And we end up with PE. So we replace P naught with PE. So we have PE here. And then all we have left over is pi R times pi C times pi T. And then the PE's cancel. And then the other assumption that we need to make, so let's just label these here, assumptions. I'll like highlight that in orange. The other assumption that we need to make, is that the compressor and the turbine are behaving isentropically. So compressor / turbine, isentropic. That means that, like I said before, pi c is equal to tau c raised to the power of gamma over gamma minus 1. And same with the turbine. Pi t is equal to tau t raised to the gamma over gamma minus 1. Okay, and we actually already know that pi r is equal to tau r raised to the gamma over gamma minus 1. That's just the definition of pi r. Remember, pi r is pt naught over p naught. Okay, so if we sub these things in, that allows us to essentially solve for the Mach number at the exits, me squared, as 2 over gamma minus 1 times this quantity tau r, tau c, tau t minus 1. Okay, and then we can see that our Mach number ratio that we needed to find for that component of the thrust expression is equal to me over m naught. It's equal to tau r, tau c, tau t minus 1 over tau r minus 1. Okay, so that's one piece that goes in there. Now let's deal with the temperature ratio. So now TE over T naught is what we want to find. So we know that TE is equal to T naught times tau R times tau D times tau C times tau B times tau T times tau nozzle. So we know that the diffuser and the nozzle both go to 1, right, because they're isentropic. And we can write TTE basically following the same sort of logic that we did for the pressure. So we can write TTE as TE times 1 plus gamma minus 1 over 2 ME squared. And we can bring in what we have from here, where we have T naught, tau R, tau C, tau B, tau T. Okay, but one thing that we have here, actually, remember this relationship that we have here, this thing. From that, we can actually replace tau R, tau C, tau T with this quotient, this object, with this guy right here. Okay, so because pi r, pi c, pi t is equal to 1 plus gamma minus 1 over 2 me squared raised to the gamma over gamma minus 1, we have made this isentropic assumption, so we can get rid of that exponent and write the product of tau r, tau c, and tau t in terms of just that value right there. So that makes things a lot more simple, where you have TE 1 plus gamma minus 1 over 2 ME squared. And then here we have T naught. And then remember, tau R, tau C, tau T. Those all just be, and then I'll put the tau B here. Those all become 1 plus gamma minus 1 over 2 ME squared. And so those things cancel. And what we end up with is that tau, TE over T naught is just equal to tau B, which I'll remind you is TT4 over TT3. Okay? For the ideal turbine. So that's real nice. We can rewrite this in terms of the engine parameters as tau lambda over tau R times tau C. Okay, and that's because tau lambda, just to remind you, is equal to TT4 normalized by T naught, and tau R is just TT naught over T naught. Okay, so that's how you get that relationship for T over T naught in terms of the ratios. Okay, so now we can write our thrust. So our non-dimensionalized thrust, in terms of our engine parameters, is 2 gamma over gamma minus 1 times tau R minus 1 times the quantity 1 plus F times tau R, tau C, tau T minus 1 over tau R minus 1 times tau lambda over tau R tau C. That whole thing raised to the 1/2 power minus 1, close bracket, and then that is the non-dimensionalized thrust for the ideal turbojet. Okay, and then we can always find F using the energy balance across the burner. So what I mean by that, well, you take m dot A plus m dot F times HT4, and that has to be equal to m dot A HT3 plus m dot F HF. Okay, and that allows us to obtain 1 plus F. So if we normalize by m dot A on both sides, you get 1 plus F tau lambda equal to tau C tau R. So we've done more than just normalize by m dot A, but by a bunch of temperature values as well. And that gives us F equal to tau lambda minus tau R tau C over tau F minus tau lambda. Okay? And that's a little bit more general. That should work across the burner in general if you want to write F in terms of those engine parameters. Okay? And so in the end, we can say that the non-dimensionalized thrust, T over P naught A naught, is some function F of tau R, tau C, tau lambda, and tau T. Okay, but the turbine and compressor are not independent. So there's an energy balance between them, right? So T and C, not independent. We have this energy balance, which is that m dot A plus m dot F times Cp T4 minus TT5 is equal to m dot A Cp TT3 minus TT2. Okay, And so if we perform all of our normalizations that we've been doing, you get 1 plus F times tau lambda 1 minus tau T is equal to tau R times tau C minus 1, which gives us tau T in terms of tau C and the other energy parameters, tau T equal to 1 minus tau R times tau C minus 1 over 1 plus F tau lambda. Okay, and so we can actually sub that back in, and I'll go ahead and do it to get a final sort of consistent expression here. Is for T over P naught A naught, which is 2 gamma over gamma minus 1 times tau R minus 1 times the quantity 1 plus F times tau lambda minus tau R times tau C minus 1 minus tau lambda divided by tau R tau C all over tau R minus 1, that whole thing raised to the 1/2 minus 1, close bracket. Okay, and in essence, you just optimize this guy, maximize this to get an optimal tau C or compressor ratio. Okay? So let's do that. So if we were to take the derivative of that thing with respect to tau C, so d by d tau C of tau lambda minus tau R tau C minus 1 minus tau lambda over tau. The taus and the lambdas are starting to mix again. Tau R tau C divided by tau R minus 1. What you obtain there is 1 divided by tau R minus 1 times negative tau R plus tau lambda over tau R tau C squared. And then since we're optimizing, we're going to set that equal to 0. And that gives us an optimal compressor ratio, compressor temperature ratio for the for the ideal turbojet of the square root of T lambda over tau R. Okay, and so what if we actually plot this, the non-dimensionalized thrust as a function of tau C, then let's say that we start at 1 here, then what it looks like is like this. It goes up for a bit, and then it's just kind of dives down. Okay, and so your maximum tau C star lives right there. Okay, and so your lower Mach number increases the optimal compressor ratio. So in other words, at a lower speed, the compressor needs to work harder. That sort of matches what your intuition should tell you. Okay, and then once your tau R reaches the square root of tau lambda, then the compressor stops helping. Okay, so meaning tau R goes up with your speed, and if it reaches tau lambda, then your optimal compressor ratio is just 1, and at that point, there's no point in having a compressor, right, at all, because the optimal compressor ratio is to not do anything, and at that point you would just want a plain old ramjet. Okay, so let's just write down a couple of those thoughts. So lower M naught means compressor needs to work harder. Nice. And then tau R approaches the square root of tau lambda. Just use a ramjet. Whoops. Compressor is not doing anything. Okay. All right. So there's some more things to discuss here, but I think that for now, I'll call it for this lecture. Next time we will go over some more engine matching conditions and some non-ideal factors when there are losses in the compressor and turbine, as well as talking a little bit about capture area, and then we'll probably do a nice big example with the turbojet. Okay, so I hope you enjoyed this lecture. I think it was a little bit more interesting than they've been. But yeah, I think I had a nice turbojet video that I showed in person when I taught this the first time. I will link that in the description of this video, so you can go ahead and watch that. There's some really great visualizations there, give you an idea of what the actual turbine blades look like, for example, and so on and so forth. Okay, so go ahead and take a look at those. That should be interesting. And otherwise, I will see you next time. Hope you have a great day.